I want to talk a little bit about grid aspects and grid integration. I mean, previously, right, the battery was more or less the bottleneck for most EV charging, at least for fast charging. But this was an individual problem. But now, I mean, as anticipated, I mean, has long been anticipated that the wide rollout will actually challenge the grids. And I mean, just as a summary, I mean, there are a few challenges that are maybe more widely known and publicly discussed, but some that are way more pressing and interestingly not discussed. One big issue has been combined the keyword vehicle to grid is particularly energy and power availability. So do we actually have the power at the time when needed, when you want to charge? Because the integration of electric vehicles, and not just that, right? Practically the electrification of everything right now, right? To make it compatible with renewable energy that's mostly just available electrically, will increase the demand of electricity by a lot. Vehicle to grid was a keyword that would say that you adjust, for example, charging to the availability, and maybe even let cars act as energy storage systems. We'll talk about it a little bit later. Just one keyword that is very important. Vehicle to grid is not necessarily grid supportive. Actually, in the way how it is implemented right now or will be implemented soon, in other cases, is likely not grid supportive at all. Because it deals mostly just with the first point on that list, right? Energy and power availability on a global scale. Vehicle to grid, how it's often considered right now with in most countries where variable tariffs are rolled out, so that instead of previously buying electricity at home, for example, charging at a fixed rate, always the same level per kilowatt hours, you could get a variable tariff and you pay essentially the price at, for example, from the current spot market price at the energy exchange, which used to be just wholesale price in the past. And on top, you get various surcharges, for example, grid surcharges. The problem is just this is a global energy price, right? That does not include in the price any aspects of grid overload that you have locally. That are externalized costs, and therefore there is also no motivation for you to adjust your behavior, your charging, whatever, to the problems of the local grid. So which problems can we have there? I mean, one thing is just overload of equipment and the capacity limits. I mean, how much can you actually locally get without bringing down your grid? That is mostly right a heating problem and protection problem and so on. Because interestingly, right, in the past, the electricity system was designed in a way that you could draw for a short time way more power than your average power would be or could reach. Because right, we never assumed that everybody will need peak power at the same time. But you also have dynamical problems. It starts with voltage band violations. That means, right, you turn on your charger, the voltage of the grid, right, the AC voltage, whatever, 230 volts or 110 volts, comes down during the entire time when you draw current and goes back up when you stop charging. That has become a major problem because grid impedance is rather rising than decreasing due to the massive electronification of everything. We'll have a look at that in a second. Voltage instability, so not just the voltage amplitude will respond to your charging, but your controller will potentially interact even with that grid voltage through the grid impedance. And that can in many places actually bring current grid chargers or current vehicle chargers to the limits, so they become unstable. That starts with filter resonances. We'll look at them in a second. And when you have several chargers or a charger in other electronic systems that are feedback controlled, their feedback loops start to interact through the grid impedance. And as you know, if you have a first order controller, but several of them, you end up with a high order resonance system. So what has changed in the last couple of years? Why do we suddenly have grid problems? I mean, this is how the grid used to be in the past, right? We had a hierarchical system. Power was mostly generated on the higher voltage levels and then trickled down through the medium voltage distribution grid into the low voltage grid, where, for example, home chargers and, let's say, medium power chargers can be connected. The nice thing there is also that the power flow was fully controlled, unidirectional, and most loads and sources were not electronic. So light, heating, mechanical sources and sinks. And you had these nice bottlenecks here at the transformer, right, where you could fuse the entire system. You could give every house a larger fuse, for example, whatever, 50 amps or so on. The entire feeder might just allow for 200, 400, 600 amps. So that might be just a fraction of n times the 50 amps that the houses have. But since you have the bottleneck here, you can give every house a little bit more because you assume they will never use peak power at the same time. And if that ever happens and would overload your infrastructure, you have here the choking point and can turn it down. However, now the grid looks more like that, and you have suddenly also sources down there. High power sources, high power sinks, right? A 10 kilowatt solar system is no longer something special. And there are suddenly power flows that the grid operator hardly sees, at least not in real time. You have injection on all levels of the grid, and everything is electronic. What does that mean? Electronics have, for example, no voltage support. They expect a fixed grid voltage, perfectly sinusoidal, nice frequency, good amplitude. They synchronize to it and then just suck or inject something and don't care how the voltage looks. And that's the difference, and that might have to change. Otherwise, we'll run into trouble. So on top of that, as I already said, in many places, I mean, this is just a typical condition, what we already have in definitely in Europe, but also other parts of the world, that this is a measurement at a distribution transformer, so medium voltage to low voltage, right? You have the typical peaks in the morning when everybody gets up and gets ready for work. Nobody's at home around noon. In the evening, you have usually highest peak, right? When everybody comes home, starts cooking, TV on, and so on. But what changed is that here. You see, this transformer has about as much load around noon, but in the opposite direction than it has in the evening peak, because the power is flowing from solar systems back into the medium voltage grid. And what it can lead to in the grid, right here again, high voltage, medium voltage, low voltage, that you suddenly have power flows that the grid operator did not expect. For example, you have a solar system here and a charger next door, and suddenly there's a current flowing from here to here that the grid operator was not expecting and is not even seeing, because all monitoring usually happens here. What's always said, right, with smart grid meters and so on, forget about it. That is usually very granular, very rough, and for privacy reasons and so on, there is often not a direct connection that your grid operator would see how much power you need or use right now in real time and what's going on there. But that might overload, for example, some lines here, and the voltage can do weird things that the grid operator only sees it indirectly through state estimation. And right, the first problem is already that you easily leave the tolerance voltage band. Right? Injection increases the voltage, power you draw reduces the voltage. But it should stay within a plus minus 10% limit, but this is until your socket in the wall. That means that many grid operators want to keep it within plus minus 5%. And here you see a typical situation, what can happen here, right? Particularly when you have, for example, at the end of a long, right, here's medium voltage, low voltage, a long feeder. At the end, for example, some new buildings attached, they get solar systems, they want to have charges and so on, and suddenly run into voltage violations. You might also overload some lines because, right, solar system here and some charger here, and suddenly you have lots of load on one line. So that were more static problems. Let's look into dynamic problems. Let's assume we have here chargers. For example, here's a standard charger that might be already a charger that's designed for weaker grids, has its own storage with a battery, and still that might not work out that well. So what's the problem? What can go wrong? Here you see, right, grid interface, DC-DC, with isolation, and then the final DC-DC for the car, for example. So that's the stage that can cause trouble. Here you see a measurement of a real charger that went berserk. You see, this is what can happen already in Europe. In a grid, you measure three-phase AC. What you expect, right, is perfectly sinusoidal voltage, and what you really get is that mess here. Particularly, right, if the grid impedance is high. And you see the charger is drawing current and even influencing the voltage, and other systems might be connected to the same point of common coupling. And you see the whole thing looks worse and worse and worse, and at some point it anyways collapses. The charger can keep relatively sinusoidal current for a while, but you see here the whole thing just can't take it anymore. You see it here already, and the whole thing collapses and goes into some protection and essentially brown out. So what can be reasons for that? Yeah, there's a couple of things that are tricky now. The grid thread has an increasing impedance now with the massive electronification. Why is that the case? Well, your chargers, all your power supplies and so on are electronics, switch model electronics, solar systems use electronics, your charger uses electronics, and they're usually constant power. If the voltage decreases, they do not necessarily adjust themselves like a conventional load, but they control it, for example, to constant power and adjust the current just to keep the voltage keep the power constant. What's the problem with that? In solar systems, right, if the voltage decreases, they don't over proportionally increase the current like a synchronous machine would be, but they at best keep the power constant, and therefore they hardly contribute to the voltage stability. They just run constantly no matter what's happening, the same 10 kilowatts, for example. And the consequence is that the impedance get higher and you get interaction, for example, between your filter, for example here, second order filter, LCL, with the grid impedance, and that can pull your resonances to pretty low frequencies. And as soon as they reach into the control bandwidth of your grid inverter or rectifier, you can run into terrible oscillations. Next thing is you get positive feedback here. Here is now two chargers shown, right? Let's assume we look at that charger, and that charger here is just turned on, and draws some current. That means, right, the voltage here at the point of common coupling will decrease. The other charger, however, is already charging, wants to keep its power constant. Voltage decreases, that means it increases its current, and the voltage decreases further. The other charger is also then by that time already in constant power, so it will also then suck harder and increase the current. You see, this leads to positive reinforcement and can destabilize your grid locally. So the various chargers can contribute to grid stability in some way or the others. I mean, there are keywords that are discussed regularly. I mean, the standard vehicle to grids, right, which is more interesting maybe at home. Although there is not necessarily an economic case to use your vehicle battery as a grid storage, as a dedicated grid storage battery is way cheaper per cycle than your car's battery. But as soon as you have both a bidirectional grid interface and bidirectional DC-DC or isolation stage, right, you can use your car as grid storage for vehicle to grid. More interestingly, are for stability, right? For dynamic stability is, for example, things like inertia. Inertia for frequency support, which is not necessarily so important locally. This is a more global grid problem, but locally, particularly voltage support. That is something, interestingly, what your charger can already do if you have a unidirectional interface, because right, you act relative to your current power. If you just want to give it a quick power boost, the local grid to stabilize it, and you're charging right now at 20 kilowatts, well, you just have to go relative to that baseline. Depending on topology, right, you can also filter, deal with the imbalance between phases, and for the later ones, right, full grid forming, short circuits, current supply, and black start support, you typically need a bidirectional grid interface. So
I
control-wise,
interject for 1 second, Stephan, if I can. We are coming up on the 11 a.m. mark here, Eastern Standard Time. So I just wanted to thank everybody who did attend the webinar and who needs to drop off. We're going to keep going, wrap up the presentation. And I know we didn't have time for Q&A, but we did have some great questions. So we will definitely do a follow-up. Just wanted to mention that. And if you need to drop off, we of course understand, but we'll be here finishing up the presentation for anybody who can stay for a little bit longer. So please go.
So control-wise, I mean, conventional control is you have usually relatively independent controls of grid interface and the vehicle side, and they mostly interact, for example, through the DC link voltage and for that topology and maybe the available power. What is already implemented in various jurisdictions, right? The distribution grid operator can influence how much power you're allowed to draw at a certain time. On top of that, latest chargers also have to monitor the grid voltage and be able to provide reactive power. What's the idea behind it? Well, to stabilize the voltage. Keep in mind, we have here grid impedance. If the grid impedance is inductive, reactive power can stabilize the grid voltage. There's just one problem. The grid is in many places not very inductive. If you have ground cables, weak grids are usually mostly, and weak grids are the most important application for voltage support, are mostly resistive. Overhead lines, right, long overhead lines, which are in more rural areas, can have enough inductance for that method to work. But future chargers might actually want to implement either full virtual inertia and or grid forming. And as I said, this is not just for frequency support. This is what's mostly discussed in the literature right now, right? That power electronics should provide frequency support. But this is a global problem. We have right now with chargers way more a local problem of your local distribution grid, for example. And for that, we don't care about frequency support at all. It's mostly just voltage support. Keep the voltage at the right amplitude, stable, sinusoidal, and avoid the high impedance or grid impedance interactions between various chargers, your charger with the grid impedance, and so on. And with that, I want to hand over to Sebastian Rivera again.